Okay, welcome to Geosynthetics. Okay, introduction. So, ano nga ba ang geosynthetic? So, let's have some basic definition. So, geosynthetic is defined as a planar product manufactured from polymeric material that is used with soil, rock, and other geotechnical related material as an integral part of civil engineering project, structure, or system. So these are polymeric materials like plastics, and according to Dr. Robert M. Corner, there are 8 types of geosynthetics: geogrids, geotextile, geonets, geomembranes, geosynthetic clay liners, geopipe, geofoam, and geocomposite. Okay, so this is a geotextile sample. So we have woven, non-woven, needle punch, and non-woven heat bonded. The geomembrane. So this is a geomembrane. So geogrid. So this is a geogrid which is commonly used for reinforcement. This one is geonet, which is commonly used for drainage. Geosynthetic clay liner. So the use of this is same with the geomembrane for containment purposes. This is a geofoam. So usually it is a good filler in reinforcement. And geocomposite is the combination of different geosynthetics. Geocell is a reinforcing since it confines the aggregate and soil. So geocell parang kulungan. Geopipe, so this is for drainage. MSE wall. So as you can see in this figure, so we have this. This is a geogrid which is acting as reinforcement, and this is the facing wherein we anchor the geogrid, and this is the backfill. So what they're doing here is they are filling up the backfill here, okay, for the retaining of this structure. So this is usually used to stabilize the slope. So this is a bridge abutment. So using MSE wall. abutment is like a column of the bridge. Okay, so these are the example of the facing or fasciae of the mechanically stabilized earth wall MSE. So you have modular blocks. So as you can see, we have here the block peel, and the layers of geotextile, okay, underneath this block peel, as shown in the previous slide. This is the modular panels. Okay, so usually we can observe that on the flyovers. Inside them is backfill. So this is a configuration of geotextile in a MSE wall. So the geotextile is overlapped. Okay, so it is wrapping around on the backfill. So that is a wrap around facing. So we're looking at the profile of an MSE reinforced by geotextile. This one is the profile of the MSE using the modular block. Okay, as observed in the previous slide. So these are your geogrid reinforcement, and this is your masonry units as fasciae. And this is the example for geogrid reinforcement with precast panels. Okay, this one is the detailed. Okay, this is much more detailed because you have other materials, not only the geogrid, but also you have this other materials such as this support strut, which is made of steel. Okay, and this one is the embedment depth of MSE wall. So embedment means the wall. Okay, you're going to dig on the ground and put foundation underneath the ground, and you put the wall over that foundation. So it is embedded underneath the ground. Okay, so these are some of the configuration with regards to MSE retaining wall. The height H, the depth Z, and then we have this L, or the length L and R, which is based on this failure surface. Okay, so that is Rankine, using the Rankine theory. And the effective LE, or the effective embedment, or the embedment length of the reinforcement. So LNR is simply the length, okay, from the face to the failure surface. LE, on the other hand, is from the failure surface up to the required embedment length. So this is similar to the development length in RCD. Also, we have this SB, which is the vertical spacing between the reinforcement. So this T is basically the reinforcing force. Okay, so that is the resistance, because you want to resist the possible failure of this surface. So if you have this failure surface, it means that this triangle will erode. So for you to prevent that, you need this reinforcing here. Okay, due to this geosynthetic, to resist the possible erosion made by the failure surface. Okay, so some of the given parameters for the MSE wall, we have the surcharge Q. So these are the load on the top of the backfill, the properties of the backfill, unit weight, angle of friction, cohesion. Usually backfill is cohesionless. And your reinforcement, you have this, the strength, then the foundation soil. So you have unit weight, angle of friction, and normally foundation has cohesion. Okay, and that's it for reinforcement. So some of the parameters used in the design. Okay, this one is based on the possible configuration of the MSE. So the designer tried to optimize, the design by simply having different weight of backfill. So not the usual rectangular. Okay, so here you have different weights, which could possibly be useful, in terms of the analysis of stability. So as you can see here, the length, the length of the geogrid is different. The top portion is 0.5 meters, the middle portion is 0.4 meters, and the bottom layer is at 0.3 meters. So that's the optimization made by the designer. This one is a reinforced soil slope in construction. So usually it is applicable in the design of highway that needs embankment, because the terrain is not uniform. Some terrains are flat, some terrains are rugged. So basically, when you are constructing a highway, so you have to, as much as possible, the stiffness of the road is not too stiff. It should be almost gentle. Okay, so that it will not be that uncomfortable when you're driving. So this is an example of reinforced soil slope. So there is a little bit inclination. So there are inclination here, unlike the wall, wherein the wall is vertical almost 90 degrees most of the time. Then you have this for drainage purposes, since you don't want your water to influence too much the strength of your reinforced soil slope. Okay, this one is the flowchart of RSS design. So the first one is establishing geometric loading and performance requirement for design, and then the determination of engineering properties of in situ soil, determine the available properties or the properties of available field, and then evaluate the design parameter for reinforcement. So next is the checking of unreinforced soil slope stability, and then evaluate design parameters for reinforcement. So the tensile strength, vertical spacing, number of layers, and the length of reinforcement. So you have two types: extensible, so that is geosynthetics; inextensible, like metal strips. And then check the external stability of reinforced slope. External stability check is like the external stability check of when you're designing a dam. So you have the check for overturning, check for sliding, check for bearing. So those are some, right? So you also have the settlement, and then yung seismic. Okay, so then evaluate requirements for subsurface and surface water control, and then develop specification and contract documents. So I guess we have a comparable flowchart made by our DPWH, because they are the ones doing the highway and public works in our country. Okay, so this one is showing us, okay, the failure cylinder or the failure circle of the slope. So the concept of the failure circle was made by the Swedish engineers. Okay, so that is the theoretical failure. Okay, the failure plane made into the slope. The simplest form is usually the plane or the wrong kind, which is using straight line. But here you can see we have an arc of a circle. Okay, so this is the coverage. Okay, so this is the coverage of the reinforcement, but this one is the critical zone. Okay, so that's why you need to make sure that the factor of safety of unreinforced is made to be resisted by the reinforcement, such that we could increase the factor of safety. So in this example, we have the configuration of external stability check for sliding. So this force PA, which represent the active soil pressure, will be in such a way, will try to push the this backfill, which represented by this trapezoid, and these broken lines here are the reinforcement, and this W represent the weight of the entire backfill. So wherein you have the dimensions such as the length at the top and length at the bottom. And this one is the deep-seated slope failure. As you can see, this failure arc or circle, okay, goes beyond the slope itself, so it runs deep. Okay, it runs deep on the foundation of this reinforced soil slope. So that is one of the possibility, okay, because this arc represent the arc of failure surface that can induce the soil erosion of this reinforced soil slope. Okay, so this one is the lateral squeeze, maybe because due to the weight of this soil slope, and then the soil underneath is soft soil, so the tendency is when you squeeze here, it will have lateral squeeze somewhere here because of the weight of this reinforcing soil. for this one. So the portion here is bigger as compared to the bottom with a smaller coverage. Basically that is the idea. This one is for the filter and drainage, because filter and drainage is important usually for the design, because filter, you don't want the bigger particle goes to the smaller particle. So just in this case, you wanted to separate the base course with the subgrade. So for you to have a structure with high integrity, okay, so some portion should not mix. Okay, so you have here the geotextile, and then the aggregate, and then the subgrade. So you don't want these two to combine, because there will be destabilization if you combine them. So the geotextile act as a filter. Okay, so to make sure that they were separated. Okay, so you can see here, these are the gabion basket wall, and then you have this so the geotextile filter is here, so this one. Okay, this one is an example of the grain size distribution of backfill. So this is almost straight line, which means it's a good, that's almost a good grain size distribution. So it's a good grade. So to summarize, so these are the summary of the geosynthetics. What are the polymer types they are made of, what are the main functions, and example of application. So we have the geotextile have 6 main function: separation, reinforcement, filtration, drainage, containment, protection. While geomembrane containment, GCL containment. So some are just single function, and some are versatile like geotextile. Geocomposite also have 6. So basically the geocomposite tries to get every advantage from the other materials, or rather from the other geosynthetics. And then we have geocell and geopipe. And these are for the design purposes: strength reduction, the reduction factors. So these are useful when we tackle the design of geosynthetics. And these are the embedment length for reinforcement. So this is also useful when we are doing the design. So for example, the layer numbers. Okay, and you have the LE. Okay, and this one we use the values. Okay, so we use 3 layers: the top layers, the middle layer, and the bottom layer. So the depth Z is measured from the top, so meaning 0.5, tapos you add this with this, you get 1, and then you add his with this, and 1.5, you add 0.4, 1.9, you add 0.4 to 0.3, and so on and so forth. And then this LE is made or resulted from the formula for LE. And based on standards, the minimum LE should be equivalent to 1. And for L and R, this one. And for the total, we just simply add the two portion. Okay, and basically for this one, we just rounded up. We just rounded up to 4 meters. And for this one, we rounded up for 3 meters. And this one, we rounded up for 2 meters. Okay, so these are the reduction factor for the design of reinforced slopes depending on the polymer type being used. And this one is the strength property requirements for geotextile filters and drains.